Welcome to our quantum deep dive.
Great to be here.
Today, we're plunging into a really fascinating intersection. We're talking artificial intelligence and quantum computing.
Two massive fields colliding.
Exactly. And our focus, it's this groundbreaking idea, quantum-assisted dimensionality reduction for efficient AI. We're basing this on a really compelling essay by Jurgo Schnepp.
Yes, a great starting point for this topic.
Our mission, really, for this deep dive is to unpack the big challenges AI faces with these enormous datasets, and then reveal how, well, the weird and wonderful world of quantum mechanics might just offer some revolutionary solutions. Almost unimaginable ones, perhaps.
It certainly feels that way sometimes.
You know how AI has just completely changed the game, right?
Yeah.
Drug discovery, financial analysis. It's everywhere.
Absolutely transformative, no question.
But, and it's a big but, with all that power comes this huge bottleneck. It's the sheer volume, the complexity, and specifically the dimensionality of the data. Think about trying to find, a specific needle, not just in a haystack, but in a haystack that's constantly growing and has like a million dimensions. That's kind of the challenge AI is up against.
And that high dimensionality issue, as Schnepp points out, it's surprisingly common. It leads directly to what we call the curse of dimensionality.
The curse of dimensionality.
Yeah, it's a very real computational problem. Think about it. If you have data points with just two variables, maybe height and weight, it's easy to picture.
Sure, a simple scatter plot.
Right. But add a third dimension, then a fourth. Soon you're in this incredibly sparse space. The data points are miles apart, metaphorically speaking.
Okay.
And the computational effort needed, it just skyrockets exponentially with each new dimension. This makes the information less dense, that's data dilution, and it demands these huge computational costs. You often see algorithms running at ON2 complexity, maybe even higher.
Which is slow for big N. Very slow.
Terribly slow. Plus, it massively increases the risk of overfitting.
Right, where the AI learns the noise, not the signal.
Exactly. It learns the random fluctuations in the training data instead of the actual underlying patterns that generalize. It's like teaching a student to memorize typos instead of the story itself.
Okay, so let's unpack that a bit. We had developed some powerful classical tools for this, haven't we? Like principal component analysis, PCA.
PCA is a workhorse. It reduces dimensions by finding the main axes of variation.
And things like t-SNE for visualization, right? Making complex data viewable.
Yeah, t-SNE is great for seeing clusters. And autoencoders, too, those neural networks designed specifically to compress data to learn efficient representations.
They've been absolutely vital for classical AI, no doubt. But what happens when the data gets really complicated? Maybe highly nonlinear or just astronomically huge? Do these classical tools just hit a wall?
They absolutely can, yeah. For extremely large or very nonlinear datasets, these classical methods often bump up against their theoretical limits or just practical ones.
Too slow.
Yeah.
Or just impossible.
Both, potentially. The computational needs just become unsustainable. Processing might take weeks or require more memory than we have, and that's precisely where quantum computing enters the frame. It offers a completely new way to think about processing information.
A new paradigm.
Exactly. It promises to overcome these bottlenecks by fundamentally changing how the computation actually happens.
Okay, so let's talk quantum then. We hear all the buzzwords, qubits, superposition, entanglement, and honestly, it often still sounds like pure science fiction.
It can feel that way.
So for someone trying to wrap their head around this, how do these abstract quantum ideas actually become real tools? Yeah. Tools that can fight this curse of dimensionality we're talking about.
Well, the core advantage, the beauty of quantum computing for this problem is its ability to achieve what's called exponential parallelization.
Okay.
Unlike a classical bit, which is strictly 0 or 1, a qubit can exist in a superposition. It can be both 0 and 1 at the same time.
So it explores multiple possibilities at once.
In a way, yes. Think of it like this. A single classical bit holds one piece of info. A single qubit in superposition can represent or process multiple pieces simultaneously. A quantum algorithm can perform an incredible number of calculations in parallel because of this.
Right. And entanglement, that's the other big one.
Entanglement, yeah. This is where qubits get linked, deeply linked. Change one, and the other changes instantly no matter how far apart they are.
Spooky action at a distance, as Einstein called it.
That's the one.
Sure.
But what's crucial here for dimensionality reduction is that entanglement lets quantum computers encode really complex relationships between data points very efficiently. Imagine trying to map, say, the connections between millions of items in a recommendation system. Classically, that's a huge matrix.
Right.
With entanglement, qubits can represent these complex interconnected relationships more directly, more compactly. It lets the quantum computer see patterns and correlations in data that are just too vast for classical systems to handle efficiently.
Okay, that makes sense.
And then there's quantum interference. This helps amplify the probability of getting the right answer while canceling out the paths leading to wrong answers. It speeds up finding the optimal solution.
So superposition, entanglement, interference, these work together.
Exactly. They create this computational environment where high-dimensional data isn't necessarily a curse anymore. It becomes, well, almost a natural fit for quantum algorithms.
So this brings us to the actual quantum algorithms, the ones designed to do the dimensionality reduction. What are some of the key players here that Yorgo Schneepat highlights in his essay?
Yeah, it's really fascinating how these principles get turned into practical algorithms. Schneepat mentions several important ones. First, there's the quantum singular value transformation, or QSVT.
QSVT.
Okay. This is really powerful because it lets a quantum computer directly manipulate the singular values of a matrix. Finding those values classically, especially for huge matrices, is very compute intensive.
Right. That's core to things like PCA and SVD.
Exactly. QSVT offers a kind of quantum shortcut. It enables potentially much faster versions of PCA or singular value decomposition, both fundamental for cleaning up data and finding key patterns.
Okay, faster PCA. What about quantum PCA itself?
Yes, quantum principal component analysis, or QPCA. Now, classical PCA, as we said, can be slow, often scaling like 0 and 3, or worse for big, dense matrices.
Which is pretty bad.
It is. Quantum PCA, though, leverages something called quantum phase estimation, QPE. And theoretically, it could slash that runtime down to O log n.
O log n. That's an exponential speed up, isn't it?
It absolutely is. Huge difference. Think about 1 million data points. N3 is a massive number of operations, billions perhaps. Log n is tiny in comparison, maybe around 20 operations.
Wow. How does QPE work, briefly?
QPE is a core quantum subroutine. It's very good at finding the eigenvalues of matrices, which you need to identify the principal components, the main directions of variance in your data. It's like having a quantum lens that instantly focuses on the most important features instead of calculating them bit by bit.
Okay, so QSVT, QPCA,
Well, Schneepat also mentions quantum SVD, which, like QPCA, promises exponential speedup using QPE for breaking down matrices, another tool for compression and understanding. And then there's the crucial task of picking the most important features from a dataset. That's often a needle in a haystack problem, too.
feature selection, right?
Exactly. For that, we see quantum-assisted feature selection. This often uses algorithms like the quantum approximate optimization algorithm, or QAOA.
QAOA, I've heard of that one. It's hybrid, isn't it?
It is, often. It uses a mix of quantum and classical processing to find good approximate solutions to complex optimization problems. Essentially, it searches through combinations of features much faster than classical heuristics often can. Imagine trying to pick the best 10 indicators out of 500 for predicting stock prices. QAOA could potentially find a great subset much quicker.
Okay. And what about quantum kernel methods? You hear that term too. What do they bring to machine learning?
Quantum kernel methods. They're really exciting because they boost classical machine learning techniques, especially things like support vector machines, SVMs.
How do they boost them?
They tap into the quantum computer's natural ability to map data into incredibly high-dimensional feature spaces. Spaces that are just way too big for classical computers to explicitly create or work with.
So classical kernels use mathematical tricks for this, right? The kernel trick.
Precisely. They work implicitly in these high dimensions. Quantum computers can directly encode and process the data in these complex quantum state spaces. The quantum kernel estimation algorithm, for example, suggests it could calculate these quantum kernels exponentially faster than classical methods for certain problems.
Another benefit.
Better classification, especially for data that isn't easily separable in lower dimensions, but might become separable in these vast quantum feature spaces. It's like giving your classical algorithm quantum-powered glasses to see complex patterns.
Okay, this all sounds incredibly powerful in theory, but let's get practical. What does this mean for real-world applications? Where might we actually see this quantum-assisted dimensionality reduction making a difference? Soon, maybe?
That's the key question, isn't it? How do these theoretical speedups translate into tangible benefits for you? Schneepat's essay points to several areas ripe for impact. Think about image and speech recognition. These systems deal with incredible incredibly high-dimensional data. Pixel values, audio frequencies.
Fisher vectors.
Huge. Quantum PCA could dramatically speed up extracting the key features. Think faster facial recognition for security, or maybe more subtle analysis of medical images, MRIs, CT scans, potentially catching diseases earlier.
And for speech?
For speech, quantum kernel methods could make selecting relevant features and recognizing patterns much more efficient. Imagine real-time, complex audio analysis or transcription that's far more responsive.
Okay, that's compelling. What about biology and medicine?
Bioinformatics and drug development. These fields are practically drowning in data. Genomics, proteomics.
Massive data sets.
Unbelievably massive. Quantum methods could really transform things. Identifying complex genetic markers for diseases using quantum clustering, maybe? Or using quantum SVD to efficiently sift through huge protein databases to find potential drug targets.
So accelerating drug discovery.
Potentially, yes. Imagine instead of taking months or years to screen candidates classically, quantum algorithms could rapidly analyze billions of molecular structures, perhaps finding promising drug leads in days or hours.
Wow. Okay. And finance. Speed is everything there.
Absolutely. Financial analysis and high-frequency trading. The speed advantage is critical. You could imagine using QAOA for quantum-assisted portfolio optimization, finding that optimal mix of thousands of assets almost instantly.
Or spotting market patterns faster.
Exactly. Using quantum kernel methods for rapid pattern recognition in volatile market data, making trading decisions much, much faster. Even complex risk management analyzing correlations across diverse global markets could be significantly improved, giving much faster, more robust insights.
This all sounds amazing. Almost too good to be true in some ways. But where are we, really, in terms of implementation? Are these just ideas on a whiteboard, or are there actual quantum computers running these things, even in a small way?
That's a very grounded question. And the answer is, we're getting there. We're currently in what people call the NISQ era.
NISQ.
Noisy intermediate scale quantum. It means today's quantum computers have a limited number of qubits, maybe hundreds, not millions, and they're noisy, prone to errors because the quantum states are fragile.
So not perfect machines yet.
Far from it. But the big players, IBM with their Q systems, Google with Sycamore, D-Wave using quantum annealing, they have shown early proof of concept implementations. Quantum PCA, for example, has been run on IBM's hardware. It showed experimental speedups for certain small, specific datasets.
So it works, just not at scale yet.
Exactly. These aren't universal industrial scale solutions today, but they demonstrate that the underlying principles are sound. The quantum advantage is potentially real.
Okay, so if the hardware isn't quite there yet, how do we make progress? How do we work with these limitations?
Great question. And the answer, as Schneepat also points out, often lies in hybrid architectures.
Hybrid, meaning quantum and classical working together.
Precisely. You combine the strengths of both. Maybe you use classical computers for the heavy lifting of data preparation, cleaning it up, maybe even doing some initial reduction to get it down to a size a current quantum chip can handle.
Okay.
Then you pass that smaller pre-processed dataset to the quantum computer to perform the really tricky part, like the core QPCA calculation or the kernel estimation.
And then maybe back to classical for the final steps.
Yeah, or you might use a quantum kernel to generate features that then feed into a classical SVM. This hybrid approach is pragmatic. It gives us a bridge, letting us tap into quantum advantages now, even with today's imperfect hardware. It helps push the boundaries of what's currently possible.
So the path forward really involves tackling those hardware challenges, right? Keeping the qubits stable coherence and reducing those error rates.
Exactly. Decoherence, the quantum state just fading away due to interaction with the environment, that's a huge hurdle. And just getting enough high-quality qubits plus dealing with the errors they inevitably make.
It sounds like trying to build something incredibly precise during an earthquake.
That's not a bad analogy. Developing robust quantum error correction codes is absolutely critical. These are algorithms designed to protect the delicate quantum information from noise. But the progress is genuinely relentless. We're seeing constant improvements in hardware design, better control systems, new software approaches, and importantly, quantum algorithms being designed specifically for these noisy near-term machines and for machine learning tasks.
So the momentum is there.
Definitely. Every year brings breakthroughs that make these quantum capabilities feel less theoretical and more tangible.
So, wrapping this up, what does this all really mean for you, the listener? Our deep dive into Jorgo Schneepat's essay, I think, really shows that quantum-assisted dimensionality reduction isn't just some, academic curiosity or a far-off dream. It seems like a critical building block for the next wave of efficient, incredibly powerful AI systems.
I agree. If you connect this to the bigger picture, the potential is just immense. We're talking about possible exponential speedups for processing these ever-growing datasets. We're talking about potentially improving how well we can understand complex AI models. And crucially, opening up completely new applications that were just impossible before simply because classical computers couldn't handle the scale or complexity.
Yeah.
Now, challenges definitely remain. Scaling the hardware, controlling errors, it's hard engineering, but the potential payoff, the synergy between AI and quantum computing seems undeniable. It's becoming clearer all the time.
So maybe this raises a final question for you to think about. As AI keeps growing like crazy and the data it eats gets bigger and messier, what other bottlenecks, maybe ones we haven't even thought of yet, could quantum computing help us break through?
Good question.
What unexpected areas beyond finance or medicine might see a total revolution from this quantum AI teamwork? Something to chew on as you navigate our increasingly data-driven world.
Definitely food for thought.
We really hope this deep dive has given you a useful shortcut to getting informed about this really cutting-edge topic. And we want to thank Jörg Schneppert again for providing the foundational insights that shaped today's discussion.
His work is well worth checking out.
Absolutely. For more information and to explore his work further, you can visit schneppert.de. That's FSCH-NEPPAT.de. Until next time, keep exploring, keep learning, and keep asking those big questions. Goodbye.